Okay, so today we're going to be talking about writing net ionic equations. Now the word net means overall, after everything has been canceled out, after everything is finished, like your take-home pay. Say you work at a minimum wage job and you get paid $7 an hour. If you work for 2 hours, you do not get $14 because they take out taxes, they take out insurance, they take out a lot of different things. So your net pay is your overall pay or your take-home pay. So with reactions, our net reaction is overall after everything's canceled out. Let's work a couple of examples. Okay, so to write a net ionic equation, there are three basic steps. Number one, to write a balanced equation. So if you look at number 2 on your notes, it's K2SO4 plus BaCl2. So this is a double displacement reaction. In a double displacement reaction, the pluses switch places, so the K is going to switch places with the Ba. So we'll have K with Cl and Ba with SO4. Now when you're writing reactions, you have to remember what the subscripts are there for. So this 4 is there because sulfate is SO4, so that 4 carries over to the other side. But this 2 and that 2 are only there because of the charges. Ba is plus 2, Cl is minus, K is plus, SO4 is minus 2. So these 2's do not carry over to the other side. But the charges do. Plus minus, plus 2 minus 2. So the charges on BaSO4 cancel, the charges on KCl cancel. Now all we need to do is balance the overall equation. So we have K2SO4 plus BaCl2 makes KCl plus BaSO4. And to balance, there's 2 Ks, so I need 2 Ks. There's 1 SO4, 1 SO4, 1 Ba, 1 Ba, 2 Cls, and with that 2 in front, that gives me 2 Cls. Okay, the next step to writing a net ionic equation is to predict whether or not a precipitate will form. We're only going to be looking at the two products and seeing whether they are soluble or insoluble. So let's start with KCl. Okay, remember the solubility rules. You need to start with the anion and look up the anion. There's Cl minus right there. So Cl minus is generally soluble except for compounds of silver, lead, and mercury. Since this is not silver, lead, or mercury, that means this one is soluble. Okay, the next one is BaSO4. So with BaSO4, again, we're going to be looking at the anion SO4 sulfates. There they are. Sulfates are generally soluble except for compounds of strontium, barium, lead, and mercury. Check that out, barium right there. So normally sulfates are soluble, but in this case, this sulfate will be insoluble, which means that barium sulfate will be my precipitate. Precipitate, fancy chemistry word for solid. Okay, so now that I have a balanced equation and I know which one is my precipitate, that is BaSO4, I'm going to write what happens in the actual reaction. Okay, so K2SO4 is aqueous. Aqueous means it dissolves in water. It's completely soluble. So really it exists as 2 K pluses and an SO4 minus 2 in aqueous solution, dissolved in water. Now the reason why I said 2 K pluses is because that 2 is there only to balance the charges. There are 2 Ks because of SO4's charge. But I did not write 4 SOs because that 4 is there for the identity of sulfate. So the 2 goes in front of the K, it does not go in front of the SO. Okay, so BaCl2. Again, this is aqueous. It's dissolved in water. So in the reaction, that's a Ba plus 2. And 2 Cl minuses. 2 Cl minuses, not a Cl2 minus. So for my products, anything that's aqueous or soluble or dissolved in water gets split apart completely. So that's 2 K pluses and 2 Cl minuses. This 2 will distribute to the K and to the Cl. And then the last one, that's where it gets tricky because BaSO4 is insoluble. It is a precipitate, it is a solid. So it does not break apart in solution, and it stays as BaSO4. So now all I have to do is cancel out what appears on both sides. I see that there's 2 K pluses on the left and 2 K pluses on the right. I see that there are 2 Cl minuses on the left and 2 Cl minuses on the right. So I end up with Ba plus 2 plus SO4 minus 2 makes BaSO4. There I go, Ba plus 2 plus SO4 minus 2 makes BaSO4. One note real quick is that something like Cl will always be Cl minus. It'll be ionic. We're looking for things that dissolve in water. It will not be Cl2, which is diatomic, because we're talking about chlorine dissolved in water like sodium chloride, not chlorine gas. Okay, let's try another example. All right, so the next one says NaNO3 plus KCl. Our first step is to write a balanced equation. So first thing is, since it's double displacement, the pluses will switch places, so the Na will be with the Cl, and the K will be with the NO3. Again, we are carrying this 3 over because that's the identity of nitrate. So now we do need to look at the charges again. Na is plus, NO3 minus, K plus, Cl minus, Na plus, Cl minus, K plus, NO3 minus, so the charges are going to cancel out. So there's my balanced equation. Now that I have a balanced equation, I need to predict whether or not a precipitate will form. Again, we're looking only at the products, NaCl and KNO3. So let's start with NaCl, look at the anion Cl minus, and Cl minus is generally soluble except for silver, lead, and mercury, which we don't have here, which means this is soluble. With KNO3, looking at the NO3, nitrates, there they are. Nitrates are generally soluble. There's no exceptions, which means nitrates are always soluble. So both NaCl and KNO3 are both completely soluble. Okay, so the next thing is, if a precipitate does form, write the net ionic equation. Since there's no precipitate, that means there is no net ionic equation. But let me show you why. Okay, so remember that NaNO3 is aqueous, so that means that in water, NaNO3 breaks up into Na pluses and NO3 minuses. KCl is also aqueous, which means in water it breaks up into K plus and Cl minus. We just determined that NaCl and KNO3 are also both aqueous, so in water that'll be Na plus and Cl minus, K plus, and NO3 minus. So when I go about trying to cancel things, the Na plus appears on both sides, the NO3 minus appears on both sides, the K plus appears on both sides, as does the Cl minus. Since everything appears on both sides, everything cancels out. There is no net ionic equation. Okay, let's try one more example. For this last problem, I want you to pause here, try it on your own first before you go back and hit play to see what the final answer is. Okay, so now I'm on number 4. I've got MgBr2 plus LaOH. My first step is to write a balanced equation. So again, a double displacement, the pluses will switch places. Mg will go with OH, and Li will go with Br. Since this 2 here behind Br is not because of the identity of bromine, it's not because bromine is diatomic, but it is because of the charges, that 2 will not carry across from the other side. There is no 2 there, none at all. Make it go away completely. So, we do need to carry the charges to the other side. Li is plus, OH is minus, Mg plus 2, minus, plus, minus. So essentially that 2 is actually staying with the Mg, not the Br, because since OH is minus 1, now we have OH2. To get an overall balanced equation, there are 2 OHs, so I need 2 OHs. That gives me 2 Lis, so I need 2 Lis, which gives me 2 Brs, but I already have 2 Brs, and 1 Mg. So there's my balanced equation. Next step. Now I've got to predict whether a precipitate will form. Again, I'm looking only at the products. I can assume that the reactants are already checked and they're already soluble. So I have MgOH2 and LiBr. Let's start with OH hydroxides. So there they are down at the bottom. Hydroxides are generally insoluble except for ammonium, group 1, calcium, strontium. None of this is those, so that means this is insoluble. This will be a precipitate. Okay, what about LiBr? Br, bromides. Oh, there they are. Bromides. Bromides are in the generally soluble category, except for silver, lead, and mercury. Lithium is not silver, lead, or mercury, so it is soluble. So MgOH2 is going to be my precipitate. Next thing, if a precipitate does form, write the net ionic equation. So I'm going to circle this guy so I don't forget that he is the one that's going to stay together. MgOH2 will not split up in an aqueous solution. Everything else will. Everything else is aqueous. So I have Mg plus 2 Br minus plus 2 Li plus 2 OH minus. On the other side, MgOH2 does not split apart, it stays together as a solid, but LiBr does. That's 2 Li plus 2 Br minus. Now my next step is canceling things out. I've got a 2 Li plus on both sides and a 2 Br minus. Those go away. Nothing else will cancel, so my overall is Mg plus 2 OH minus makes MgOH2. Alright, so there is my final net ionic equation. And one more time, let me remind you, these diatomic ions are not diatomic, they are ionic. Ionic, not diatomic. Because we're dealing with aqueous solutions, not gases. So Br minus, not Br2, not Br2 minus. Instead, the 2 that's down here at the bottom is only because of the charge, not for a diatomic molecule. Okay, that's net ionic equations.